Good morning and welcome to lecture number 28. In the last lecture, we looked at algorithms for MST. In particular, we were looking at Prim's algorithm. Towards the end of the lecture, we were proving the correctness of the algorithm. I'll continue with the proof from where we left yesterday. So the main statement is, okay, so just to summarize, Prim's algorithm greedily builds a tree, okay, of a subset of vertices. The way it does is starts with a vertex and then grows the tree. So you can assume that single vertex tree to begin with. What we have is single vertex tree to begin with, and then keep on adding edges which are out of the tree to the rest of the graph. Of which is of minimum weight among all candidates. Okay, so for the correctness, correctness is again kind of exchange argument. So the statement that we were trying to prove is the following. Let's say Tk be the set of edges, that is the tree obtained after kth iteration of Prim's algorithm, and Sk be the corresponding vertices. Okay, so the claim is for every k, there is a minimum weight spanning tree W such that the edges in Tk are contained in W. That is, you can, in other words, intuitively, at every iteration, the partial tree, the tree that you're having can be extended to a minimum weight spanning tree. Okay, by extending, I mean adding edges. Okay. Yeah, so the proof is by induction on K. So we have assumed T0 as the empty set and S0 as single vertex, that is 1. So the statement is trivial in that case because every minimum weight spanning tree contains empty set. Now for k greater than or equal to 1, we'll assume that the statement is true for all k prime less than k. Okay. Now we are going to focus on transition from tk minus 1 to tk. Okay, we are looking at the edge that is going to be added at the kth iteration of the greedy algorithm, Prim's algorithm. Let's call it as ek. U will be the endpoints. Okay, so the difference between tk and tk minus 1 is exactly ek. So our analysis is going to depend on how ek behaves with the rest of the tree or rest of the graph. So let's have a picture in our mind. So this is tk minus 1. This is a tree, so this will have some structure like this. And what we have is ek. So let's say this is ek. Okay, this is the rest of the graph. So v minus sk minus 1. Okay. So by induction hypothesis, we have a W. Okay, so W be the MST of G, be any MST of G, such that Tk minus 1 is contained in W. So why such a W exists? Due to induction hypothesis. Okay, so by induction hypothesis, such a W exists. Now we are going to stare at the relationship between W and Ek. Okay, so clearly if Ek is in W, we are done, because Tk is also contained in W. So we have proven what we wanted. Okay. Now we'll assume without loss of generality that Ek is not in W. That is, Ek is not an edge in W. Okay. So you can just intuitively assume, this is very similar to our earlier analysis of greedy algorithms, where you can assume kth iteration is the first place where the algorithm differs with any of the optimal solutions. It's pretty much that. Okay. So we are assuming that W does not have Ek. So W has other edges. Okay. So on. W also has these blue edges along with the green edges. Now, so let's look at the interaction between sk-1 and the rest of the graph. Okay. So since the tree is connected, right? Since W is a spanning tree, there has to be an edge between these. So remember that these are the edges also in W as well as T. Okay. Now from here, due to connectivity condition, there has to be an edge across, right? So let's call that edge as E prime. This could be E prime. Okay. Now, so one thing is, what is the weight of E prime? Can it be smaller than Ek? So look at Prim's algorithm. So Prim's algorithm was growing the tree. Okay. So currently it has blue edges. So it is growing out. So it's looking at edges outside this tree Tk-1, and it's taking the minimum weight edge among all those candidates. So if E prime had weight smaller than Ek, then Prim would have picked this one, right? So the fact that Ek was chosen means that weight of E prime is at least weight of Ek. It could be equal to weight of Ek. Okay. So if weight of E prime is less than weight of Ek, then Prim would have chosen E prime instead of Ek. So we can assume that weight of Ek is at most that of E prime. Okay. So now we add Ek to W and stare at the cycle it creates. So remember that for any spanning tree, if you add an edge, it's going to create a unique cycle, right? It's called a fundamental cycle. Yeah. So let's call it as C. So C be the fundamental cycle. So C is our fundamental cycle here. This is C. Okay. So now we just look at various scenarios here. Okay. So either E prime is in C or not. So since we so one more thing, how about Ek? Will it always be in the cycle? Anybody?
Yes.
Yes. So if you add an edge to a spanning tree, it creates a fundamental cycle which will always contain that added edge, new edge. Okay, so that is property of spanning trees. No need of minimum weight, any spanning tree. Okay, so that way Ek is contained in C. Now we are going to divide into two cases, whether E prime is in C or not. Let's first see what happens when E prime is in C. We'll talk about the second case later. So if E prime is in C, so how will you go about it? You just stare at this diagram. So here we have drawn such a way that E prime is in C. What will you do? Yeah, many of you know it. I mean, we discussed it yesterday too. So please go ahead.
Sir, we will see which one is the minimum at Ek or E prime, and we will remove. We will keep the.
That we already know, right?
Okay.
We already know, right? Weight of Ek is at most that of weight of E prime, right?
And we will keep one. We will remove the other.
This here. Yeah. So see, otherwise Prim would have chosen E prime, right? So that is why we know that weight of Ek is at most that of weight of E prime. So even if you remove E prime, we are going to have a spanning tree, of course, right? What will be the weight of the resulting spanning tree?
Less or equal.
This will be less or equal to. Okay. So case 1, E prime is in C. Then let W prime be W minus, W union Ek set minus E prime. Okay. So W prime is a spanning tree. Okay, because what you have is a spanning tree plus an edge, which is a cycle. Now we remove one edge from the cycle, it becomes, it still is a spanning tree, and weight of W prime is equal to weight of W plus weight of EK minus weight of E prime. Okay, but we have weight of EK less than or equal to weight of E prime. Therefore, weight of W prime less than or equal to weight of W. Okay, so therefore W prime is also MST. So assumption that W was an MST, so W prime must also be an MST, right? But what is the usefulness of W prime?
It is of having less
Why
weight.
did we need it?
It is of having less weight compared to W.
See, we have, yeah, that is true. It cannot have less weight as such, right? Because what we have is W itself is an MST. We started off with the assumption that W is an MST, so it can have equal weight, right? That's the only possibility. In fact, it will be equal,
Yes.
right? Yeah, but what is the usefulness of W prime? Why did we need it? Why
Contains
did we need to
EK,
construct it?
and it will prove our induction.
Exactly. Exactly. So what we have is now W prime is an MST which contains TK. Okay. So W prime, so TK contains, is contained in W prime by construction. So remember that TK minus 1 was in W. The difference between TK and W prime up to this part was EK and E prime. What all we did was, even if you swap EK with E prime, that is, you remove E prime and EK for this case when E prime is in C, we have that what we get is a spanning tree, and by construction, by the choice of EK and E prime, we know that the weight of this spanning tree is smaller, but it cannot be smaller because W itself was an MST, so it is of equal weight. But the advantage is it also has EK along with the TK minus 1. That means it has W prime contains TK. So this proves the induction statement. For case 1, of course. Okay. So the first case is done. Now many of you will be thinking, okay, is there a possibility of second case? Isn't it always the case that E prime and EK both will be in the cycle? Am I right?
Sir, but how do we argue that?
Yeah, okay, so that's a good point. How do we argue that? But you still have a suspicion, right, that it may not be true.
Yeah, because Prim picks the least weight edge, and we can only say that EK is less than or equal to E prime.
That is true. So no, my question was, I mean, so is it always the case that E prime will see EK certainly is in this cycle, right? So the only other possibility is C, either E prime is in the cycle or not. So if E prime is in the cycle, we are done, right? Now the question is, the second case that we need to handle is when E prime is not in the cycle. So the first doubt, at least I have, is why is it? I mean, at least looking at this picture, so there has to be an edge across, right? So there has to be an edge across. So it is E prime. So why not E prime is in the cycle? What happens if E prime is not in the cycle?
There might be an edge which is higher weight than E prime in the cycle.
No, what kind of edge?
So you are saying
See,
that
there could be
E prime
edges.
is
These
not
edges
in
could be of
this.
higher weight, right? This, yeah.
So I'm saying this cycle is being formed. Okay, okay.
Uh-huh.
The vertex is
Yeah.
in the base.
No. What is it? Yeah. Can you be a bit clear? I mean, there was some noise.
Sir, the vertices in the V slash SK minus
Oh.
1 may not be connected, no? Then it would not be form a cycle, right? The vertices in the TK minus 1
You
would
are
be
kind
connected.
of right. So yeah. So what you're saying is, yeah, in the tree W, these vertices need not be connected. So at least the way I have drawn, these look like connected. So in that case, what will happen if they are not connected? What will we have? We'll have
We
more
don't form
edges
a
across,
cycle,
right?
right?
No, we'll form a cycle. There is no doubt about it. We'll form a cycle, but there will be more edges, no? E prime, see, right now, the way I have drawn, E prime is the only edge between SK minus 1 and rest, V minus SK minus 1. Right? So the statement that you made, if this portion is not connected, but overall W is connected, right? It's a spanning tree. How is it possible? Only ways you can have more edges. So the other possibility is you will have more edges here. That is, E prime is not only one. There are many candidate E primes. Right?
Sir, that E primes, other candidate E primes could be of higher weight than E prime. Could it be?
They could be of higher weight than E prime.
So I was saying that if your E prime is not forming a cycle with EK,
Yeah.
that higher weight edge would form a cycle with EK.
Yeah. Oh, so, okay. Okay. So you're saying it will still work. That's what you're saying, right? Yeah. I mean, yeah, I'll come to that point. So only possibilities, there are many candidate E primes. Okay. But now, did it really matter which E prime I chose here? So all I needed is E prime, which belongs to the cycle, and it should be edge across, right? See, the way I wrote the argument, I started with an E prime. Instead, what I could have done is I could just take this cycle. Okay, so that is you add EK and take the cycle. Okay, so that's exactly what we have written it here in this statement. Okay, so even when E prime is not in C, then there has to be an edge, let's call it as E double prime, such that U double prime is in SK minus 1 and V double prime is in the complement of it, V minus SK minus 1. Okay, so somehow, so because of the connectivity property, this cycle, remember that EK is connecting TK minus 1 and V minus SK minus 1. So it will have at least exactly one more edge. It could it have multiple edges? Yeah, it can go back and forth, but it would have at least one more edge so that it completes the cycle. Because the cycle starts from here, it has to come back, right? This way. So that edge could be anything. Let's call it as E double prime. Okay. So it may not be this. So let's disconnect it so that we understand. I don't know if it will. Yeah. Okay. Say this is how it looks like.
Sir, I have one question here. Hello.
Okay.
Okay.
Yes.
So
Yeah.
in the exact graph that you have written here, hello. Just consider the graph, this entire graph without EK. The green part corresponds to the minimum spanning tree, right?
Yeah, green and blue constitute W. Okay.
Okay, so aren't we having a cycle already with E prime and E double prime?
No. That's why I disconnected. So it has to be disconnected. See, the scenario I was in the best case scenario was E prime was the only edge across this in W. Okay. In that case, we are done. Okay. Oh, sorry. Okay. Yeah. Okay. But the other possibility is, see, that's not the only scenario, right? So like one of your classmates pointed out, it could be that, see, that assumption, that also equivalent to assuming that this is connected in W. V minus Sk minus 1 is connected, which is not necessary, right, in a spanning tree.
Sir, all the graphs that we are connecting, like considering, are connected, right, in Prim's algorithm?
Yes.
Okay, so I'm not understanding the part why V minus
It
Sk
is
minus 1 is not connected.
In W. So in W, if you just look at edges in W, green edges, okay, and you look at only these vertices. So if you, maybe I can just give an example, okay. So let's say, let's take some other points here. So this is my VK, okay. I can have, so this is my spanning tree, okay. Now, say one example is this. You can have, sorry, green edges, right? Okay. So this is W. Okay. This is how it is. The green and blue edges make a W, and the blue edges are Tk minus 1. So now this is my V minus Sk minus 1.
Sir, the green part is W, are you saying?
Green and blue together make W. It's a spanning tree, right?
Okay.
Yeah. So the blue part is Tk minus 1. So this is Sk minus 1. Okay. So it could be like this, right? So that means in the tree, if you combine blue and green edges, V minus Sk minus 1 is not connected. That is all it is. So in the first case, the best scenario, I was also assuming that this is connected so that there is only one edge. Let's call this as E prime. There is only one edge, which need not be correct. Because tree could be this, right? This is also a tree. This is also a spanning tree. Green plus blue forms a spanning tree. So in W, if you just look at edges of W, if you focus only on vertices which are not in Sk minus 1, they may not be connected. So here, yes, it is clear that Sk minus 1 is connected in the tree W, because that is how it is, and it also contains Tk minus 1. So that portion is Tk minus 1, hence it is connected. This portion need not be connected, right? Why should it be? All we need is a spanning tree, and this is a legitimate spanning tree, right? So that is the second scenario. In that case, when you add Ek, so let's say my Ek was this. Say my Ek was this. Okay. Suppose my Ek was this. So then E prime is not in the cycle C, right?
Yes, sir.
Yeah. So that is all. Okay. Yeah. But the point is, so I'm just saying that since what we have is a cycle, it has to go from one component to the other, right? So it has to go from, we know that it contains Ek. That means it has to come back. So suppose the cycle we started here, this node. So it uses Ek to go from Sk minus to Vk, Sk minus 1 to V minus Sk minus 1. It has to come back somehow, right? It can go back and forth multiple times, nevertheless, but it has to come back at least once. Okay. So let's call this edge as Ek minus 1. Sorry, E double prime. Okay.
Sir, how
We
is
all
E
agree with
prime
me?
different from E double prime?
Yeah, that's how we just said, okay, E prime is one edge, right? It need not be the same as E double prime. There could be multiple edges. That's all.
So when we say E prime doesn't belong to cycle, E prime is all those edges that go from Sk minus 1 to V minus Sk
No,
minus
E
1, and they are
prime
in
was,
all.
we didn't say how to pick, right? Yeah. Sorry, yeah. I lost the last sentence. Can you repeat?
Hello?
Yeah. So last sentence I could not hear.
Okay,
Can
so
you repeat?
yeah, as you were saying, we did not pick specifically which edge we want from sk-1 to vk minus sk-1.
Exactly. You're absolutely right. That's what I was going to say. Okay, so when I said E prime, I could have chosen E double prime. Yeah.
So can't we in the starting directly say that whenever we have an ek, whenever we add an ek to w,
Yeah.
there exists an edge e such that it
Yeah.
forms a cycle.
That is all. That is all it is. Yes.
Okay.
So I've just written it here. So there has to be an edge E double prime, whatever it is, you could call it as E prime itself, which is across sk minus 1 and v minus sk minus 1. Okay, and the point is, see all of these edges. So by the choice made by Prim, right? Prims, right? So Prims is looking at all this, and ek is supposed to be the least. So even in this case, weight of E double prime will be smaller than or equal to. So weight of E double prime will be smaller than or equal to weight of ek. Okay. So all I could have done is I need not have to choose E prime at the beginning itself. I have just looked at add ek, look at this cycle. Okay. Look at this cycle C. So we know that the cycle has to go back and forth. So because it's using ek, it has to come back to this component sk minus 1. Okay. So that means it will be using some edge. And by the choice made by the Prim's algorithm, this some edge which is used by this cycle will be of smaller weight. So you can always remove this cycle so that we still have a spanning tree. Okay. So that is all this is. So we just take w prime as w minus e w prime union ek. Now by the choice, weight of w prime is at most weight of w. And the way we have considered w, we know that tk is contained in w. So this is tk. Blue edge plus the red edge is tk. Okay, that is all. So this is very common mistake almost everyone does when argue about spanning tree. So that's exactly the reason why I've written the proof this way. You always tend to assume that there will be only one edge here, okay, which is not the case. So many of the proofs, I mean, not just this proof of correctness of Prim's algorithm, but many arguments about minimum weight spanning trees, you make this assumption that this is connected, and many of the arguments fail when this is not connected. Okay, so in this case, it does not fail; it just works fine. Both the cases, I mean, you will have an edge across, and by the choice made by Prim's algorithm, this edge across will be having smaller, larger weight than the one chosen by Prim's. So hence, you can always remove it from the cycle. That's all. Okay. Yeah. Okay. Any question? Okay, there is no question, it seems. Okay, so we are done with the correctness of Prim's algorithm. Now onwards, next 2 to 3 lectures, we are going to look at implementation of Prim's algorithm. Okay, so let's just quickly do a rough analysis of the complexity of Prim's algorithm. So what is the total number of iterations in Prim's algorithm? We are growing the tree, right? You are adding one edge at it every time, and the set S grows from 1 to n. So the total number of iterations for this while loop is n minus 1, right? So n minus 1 into something is going to be our complexity. Now, so what is the cost of this set, this operation? Yeah.
Order of the edges as such, if we name implementation.
In the worst case order of edges, right? Yeah. So number of iterations is n minus 1. In the worst case here, you'll have to search among all possible edges. So it could be order of m. Okay. But there are also slightly better implementations where what you can do is you can pre-process it such a way that for every vertex you maintain minimum weight edge going out of it. Okay. So how much time does that take? So each edge will each vertex will have degree n minus 1. So at most n minus 1. So you will have to choose minimum weight. So to begin with, this process will take order of n square time, right? Then what you can do is, so for this, you can just modify that data. So I don't have the picture. Okay. Okay, maybe I'll just do it here only. Okay. So as you go along, so let's take some rough graph to begin with. Okay. Now suppose you're growing using prims. Let's say this, and so on. Okay. So initially what you do is you have this information, the min outgoing vertex for outgoing edge for each vertex. Okay. Okay. Now, so what you do is at every iteration, so when you grow this tree, so this is my, say, let's say tk minus 1. So this list, so let's say the next edge that I choose is this. Okay. So what I do is I merge the list for these. So I'll just merge. So there is a minimum outgoing, minimum outgoing, minimum outgoing, minimum outgoing for each, right? So when I say, let's look at this step, okay? So this was the minimum outgoing from 1. So let's take this as vertex 1, okay? Now what you do, so this vertex 1 and 2, you just merge their mins, okay? Now you update, so this has some min, this has some min, so you choose this one. Now, so what are the remaining elements? So you look at this, and if this value, the min for this is smaller than min for this, you just take that as a min for your tree. Okay. If not, in that case, you will have to find the second min among this and then compare if this is smaller or not. Okay. So that processing you will have to do. So keep on doing it at any point of time. You know that whatever tree you have, so you will have, so you will have a minimum weight edge which is going out of that tree. So let's say this was my tk minus 1. Okay, so this was my tk minus 1. Then when I add this, so what is it I need to do? I need to compare with the min of this vertex as well as min of this tree. Whichever is smaller, I just keep it. And I continue. In the worst case, what I may have to do is I may have to, so in the what is the worst case scenario? Suppose this was min weight edge for this, okay? So then I won't know what is the next min. So I will have to extract that, the second min here. Okay. So let's say minimum weight was 1 here. Okay. So the second minimum weight is, let's say 3. But I wouldn't know what is 3, right? Because initially I have only kept the min. Okay. So at most, at every iteration for one vertex, I will have to do this recalculation of min outgoing edge. I'm not giving much details. I'm just giving a rough idea. Yeah, so if there are any questions, please shoot in, because we are going to further improve this. I mean, we are not going to getting into the complete details of this, but I hope the rough idea is clear. So what you are going to do is for every node, there is a min. that is minimum outgoing edge. When you update the tree, now this tree becomes one vertex for you. Okay, so you can imagine that way. So when I have this as my tree, now minimum outgoing will be minimum of outgoing of this vertex as well as this vertex. But how do I obtain that? So one way is you compare the mins and take the smaller one. But in the worst scenario, the min could have been this, just this edge. Okay, so then if you look at outgoing edges, the min could be a different number. So in this case, it could have been 3. In this case, it could have been, say, 4. Okay, say 4. But how do we get that information? We'll have to do computation of min again among all edges incident on 1 as well as 2. So for now, it's an order n operation. Okay, assuming you have adjacency list or adjacency matrix. Now, suppose you have tk minus 1. This is my tk minus 1. So inductively, you have a min. Okay, that is minimum weight outgoing edge. It could be this as well. I mean, it could be only this, or there could be other edges. Okay. Now, when we update, so what we do is we just compare it with the outgoing edges of this new vertex which is being added. Okay, so you look at all these outgoing edges, Now you look at this as well. You look at the second minimum. If there are multiple edges of the same weight, it could as well be minimum. So you compare it to the min of this. Whichever is smaller, you update. Okay. So roughly you can improvise to order n per iteration. That's all I was going to say. Okay. Well, this itself is a non-trivial implementation. I'm not going to give into the detail of it because it does not require much data structure to do it, but a crucial analysis. You'll have to analyze because you will be confused. Okay, I will be having n edges. Then won't I require? So if I have n minus, say n by 2 edges, not n minus 1, n by 2 edges here, then won't I require n by 2 into n minus 1, order of n square? You can do a bit more careful analysis. You can argue that overall it only requires order n. Okay. So
Hello, sir.
yeah,
Just
per
one
iteration you can, yes, yeah.
So for each updation, suppose we add an edge to this tree, the existing tree,
Yes. Yes.
and then we have to recompute the minimum. Since we are not maintaining any order of the edges at each vertex, we have to go through all the edges that this vertex can have. And that could possibly be n minus 1. Possibly, I'm saying. It could be a little less.
Yeah.
So, like, can you, from this context, can you tell me why it is order of n for selecting the minimum again?
Yeah, okay. So that's exactly what I didn't want to do. Anyway, so because I'll spend half a lecture on it. Okay. So see, it has to be done very carefully. Okay. You cannot, so you have to assume, for example, the adjacency matrix representation. Okay. With every representation, you cannot do. So what I can do is, so see, at this point of time, what is the information that I have? So I have among the outgoing edges, what is the minimum? Okay. So now what I can do is I can kind of merge. I can merge all this. So I can merge the adjacency, whatever, right? Adjacency matrices of all these. Okay. So I can just combine. Imagine this is one graph. Okay. So what I do is, so I look at the adjacency matrix. Okay. So let's say my first vertices are V1 to, let's say Vk minus 1. Okay. Now what I'll do is I'll merge this. So I'll merge this into one vertex. How will I do that? So this has to be done iteratively. It will be done one vertex at a time, of course. So how do you do this merge operation? You look at component wise. You keep the minimum weight. Okay. So you just imagine that this is going to be one big vertex for me, okay? And I'm only looking at outgoing edges. So at the first step, what you do, you look at the, so say you have adjacency matrix representation. I look at the adjacency, the rows corresponding to, let's say, V1 and V2, okay? So this is V1, this is V2, column V3, etc., Vn, okay? So now what I do, so to V3 there is weight of 30 here. From V2 to V3 there is a weight of 20. So what I will do is I'll just keep it as 20. To V4 there is a weight of 5. There is a weight of 2. I'll keep 2. To V5, let's say there is 1 and there is 3. I'll keep 1. Okay. So this way I'll merge these two vertices, keeping minimum weight edges. Okay, so from 1 to, let's say, 5, there was a weight of 1 here, weight of, I said 3, right? Then I'll not keep the edge 3. I'll just throw it away. I'll just keep edge 1. Okay, so that way what I can do is I can ensure that I'm having only n, at most n minus 1 edges out of this tree. So I'll have an array which consists of at most n minus 1 edges. For every iteration, how do I update this array? I can update this array by, so I have the array, we can call it, see, when I have adjacency list, it's going to be a bit painful because you'll have to worry about indexing. So when you have adjacency matrix, it's very easy. It's basically an array representation. So you have an outgoing array here, okay, which is of length at most n minus 1. Now you also have outgoing array here. Okay, so all you do is you do a merge operation this way. So this is V1 could be the array for this whole tree tk minus 1. V2 is the array for this new vertex which is being added. I mean, whose edge is being added. You just merge. It will be linear time operation.
Sir, like in summary, can we say like this?
Yeah.
Since we are contracting this tree, this and all these vertices in the tree are becoming one vertex, and hence it is order of n.
Intuitively, that is how. Yeah. Intuitively, you're doing that. I mean, you don't have to essentially that's what you're doing. Yes.
That's why it is order of n.
Yes. Yeah.
Then, but okay, but it is order of n for each new vertex we add.
Yes. So for every iteration, it can be done in order of n. Otherwise, it can be order of n square for each iteration.
So it
like you said, right?
Okay, I understood. I thought it is order of n in total, but it is order of n for each iteration.
Yes, it's order of n for each iteration. Okay. Even this you'll have to. I mean, even for each iteration to get order of n, you'll have to do this. Otherwise, it cannot be. Okay. Otherwise, what will happen is you'll have adjacency list or the adjacency matrix for each of them. Like I said, right? The size of tk minus 1 could be, let's say, n by 2. Okay, then you will have n by 2 arrays. You'll have to process each of them. That will take order of n square time. So overall, it could have been order of n cube, but you can do it like order of n square using this trick, this contraction trick. You can just imagine tk minus 1 as one vertex. Okay. So in summary, so number of iterations, n minus 1. Each iteration using adjacency matrix representation can be implemented in order of n time. So overall, it's order of n square time for prims. Okay. So whereas Kruskal's, it was order of m log n. Okay. So in particular, if m is significantly smaller than n square, Kruskal's becomes a faster procedure. Okay. So this seems to be a bottleneck for prims if we use this implementation. So however, it turns out that you can actually achieve better. Okay, you can match with Kruskal's bound. See, only non-trivial part here was this, right? So this comparison, computing the minimum. Okay, so this computing the minimum. So we needed order of n operations, right? Not just, I mean, computing the minimum, updating it further. Okay, so we'll see that using the heap data structure, we can implement what is known as priority queues. Okay, so you can, so this information extraction can be done, say, amortized order log n time. Okay, so this can be brought down to order of roughly not n log n, it can be brought down to m log n. Okay, yeah, m will come into picture because the heap or the data structure will have to store the edges, all edges. Okay, yeah, so that is what we are going to see next. Let's see how much time I have. Okay, so what I'll do is I'll give a quick overview of heaps. I believe all of you have seen heap. Is there anyone who haven't seen? So those who have done CS courses would have seen. Okay. But what I'll do is I'll spend 5 to 10 minutes introducing the heap for everybody so that all of us are in the same page. Then we'll see how to implement the priority queues using heaps so that we can improve the complexity of our implementation for prims. And then later on, we'll also see what are known as Fibonacci heaps, which is a general, I mean, extension of heaps with some certain, ensuring certain properties. We'll see that this can be matched, so we can match with Kruskal's algorithm. Okay, the complexity will be matched with Kruskal's algorithm. So in particular for huge graphs, this will be even overtaking Kruskal's algorithm. Okay. I'll give a quick introduction to heap. So formally, heap is an array object which is viewed as a complete binary tree. So basically, you have array of elements. We'll assume these are numbers comparable to each other. But we also have a superimposed binary tree structure on it. Okay. So here, each node of the tree is an element of the array, element in the array. So this is an example I have taken from CLRS. Okay, say this is array. Okay, say 16, 14, 10, 8, 7, 9, 3, 2, 4, 1. Okay, so we impose a tree structure. So we'll assume that the first element in the array is the root node. Okay, so A1 is the root node. Now the left child of array element AI is A2i. So A1, its left child is element 2 into 1, which is 2. So that is A2. So 14 is the left child. And the right child is A2i plus 1. So that is 2 into 1, which is 2 plus 1. A3, which is 10. Okay, so this is the first set. So now the right child, left child of 14, which is, I mean, A2 is 2 into 2. So I is 2 here, so which is 4. So A4 is the left child. 2i plus 1, that is A5, which is 7 here, is the right child. So similarly, left child is 2 into 3, which is 6. 2 into 3 plus 1, which is 7. That's element 3, and so on. Okay. So the condition is the tree should be almost complete. Okay. So only at the lowest level you can have leaves. So I cannot have a leaf here and go on till here. Okay. So right now we didn't impose any conditions on these values. So these values we call as keys. So these are keys. And keys could be some value that you search for in a database and so on. So we'll assume that these are numbers. Okay, so that they are comparable to each other. Yeah, you can also have keys as strings and so on. But for simplicity, we'll assume these are numbers. Okay, so this is what we said there. So parent of I, so we'll just see these as relations as functions. So parent of I is I by 2 with the floor. That is, so if you take any node, right, how do you know the parent of that node in the tree? Okay, so what is parent of element, fifth element, which has a key value 7. So here is the formula. So parent of ith nodes, I is 5. You divide by 2, take the floor. So 5 by 2, which is 2.5, take the floor, which is 2. So parent of 5 should be 2. Okay. So if you take a parent of say 8, okay. So node 8 is here. So 8 by 2, which is 4. You take floor, it is still 4. So 4 should be its parent. So 4 is the parent, which has key value 8 here. Okay. So that way, we'll just see these relations as functions. So parent of I is floor of I by 2. That is, if it is odd, then I by 2 minus 0.5. If it is even, then it is I by 2. Okay. Similarly, left and right also we will view as functions. Okay. So left child. So the left child of I is array element indexed 2i. Right child of ith element in the array is 2i plus 1. Okay, so that's exactly here. So 2i plus 1, which is 7 here. So 2i plus 1, 11 is not there. So see, if you have a complete binary tree, which is full at every level except the leaf. Okay, so all leaves are at the same level. Then you know that number of elements is going to be what? 2 power n minus 1, right? But n need not be a power of 2 or power of 2 minus 1. Okay. So what we'll assume is, so you just have tree structure, but you are allowed to have leaves only at the lowest level or just one level above. Okay. So for example, I cannot have leaf here. So this cannot be a leaf. If you want it to be leaf, you'll have to terminate here. You cannot go any further. Okay. So you cannot go up to here and have this as a leaf. Okay. So these are called almost complete binary trees. I hope people have seen what are complete binary trees and so on, full binary trees or complete binary trees. Okay. So yeah, so here the leaves are at whatever one level plus or minus. Okay, so this is say level 1, this is level 2, this is level 3, this is level 4. So if you have a leaf at level 4, then you can have leaf at level 3. You cannot have at leaf level 5, for example, or you cannot have leaf at level 2 or level 1. Okay, so that is not allowed. So now I cannot extend this into this. This is not a valid. This is not heap. Okay. Now heaps become interesting when you impose certain ordering conditions on the elements. Okay. So max heap is one where the key at the parent is greater or equal to any of its children. Okay. So that is A of parent I is greater or equal to A of I. Min heap is the other way around. A of parent I is smaller than its children. Okay. So these are the interesting cases of heaps when you impose order restriction. Okay. Yeah. So in the next lecture, we'll see operations on heaps and see how to use it for our implementation of Prim's algorithm. Okay. I'll stop now. It's already time.